Hi everyone, thanks for tuning in. I will talk about adaptive piecewise deterministic Monte Carlo algorithms, and in particular this is a joint project with Joris Bierkens. I would like to start with a bit of an introduction to the use of piecewise deterministic Markov processes for Monte Carlo sampling. So this class of Markov processes, PDMPs, has been recently introduced in this context, so in the context of sampling, of generating samples from a target density. Of this form, we will call U the energy function. And what's interesting for this application is that PDMPs are continuous time Markov processes and also are irreversible. And this property in particular can and is known to lead to a faster convergence generally of the Markov chain or of the Markov process. What characterizes PDMPs are random events and deterministic dynamics between events. At the moment, the two most prominent, the two most well-researched algorithms in this class are the bouncy particle sampler and the zigzag sampler. Just to give you a bit of an idea, if you're not too familiar with these processes, we have continuous time trajectories, which are in the blue lines here, and then we have the random events, which are the orange dots. Here in particular, we have a zigzag sampler that has as target density a standard Gaussian. But the mechanism is always the same. So at event times, basically what happens for zigzag is that one of the components of the velocity flips sign, and we can observe it here. Similarly, for bouncy, we have deterministic dynamics that are linear, and at random events, the process basically is rebounded on the level curves of the energy function. So same linear dynamics, but different mechanism at random times. These are really novel methods, so they have been introduced really in the past 4 or 5 years. And as such, there is still a lot of room for improvement, and also a lot of theoretical understanding is still there to be gained. In particular, what we will talk about in this case is really the behavior of these samplers in the case of anisotropic targets. In particular, the zigzag sampler is very sensitive to correlation in the target density, while the bouncy particle sampler is more robust to anisotropic targets, but still we will see that it shows performance degradation. So our interest here is really to modify these algorithms in such a way that we can make them better in this case, so in the case of anisotropic targets. But before starting really to propose our solution, I would like to give you an example to make clear really what are the effects of, for instance, an increasing correlation in the target density. To this end, we consider a 50-dimensional multivariate Gaussian target density, and we take this Gaussian to have the covariance matrix in the slide. And in particular, so we see between all components, there's a correlation rho, and all the components have unitary variances. What we will do then is just fix a time horizon, continuous time horizon, which will be 10 to the 4, and we perform 100 experiments for each value of rho. And what we obtain are the plots that I'm going to show you. The first one concerns the number of events that one has to simulate when simulating the processes within this continuous time horizon that remains fixed. So here we have on the x-axis the correlation, and we just let it increase up to 0.99, and we want to see really what happens. So considering that the y-axis is in log scale, we can see quite a strong increase really in the number of events that we have to simulate. And in red we have zigzag, in blue bouncy, and we see it's the same effect, but the two processes really start from different points, I would say, but the behavior remains the same. And so you can imagine that events are really the expensive part to simulate when implementing these MCMC algorithms. And that is because, in particular for the choice of dynamics we have with zigzag and bouncy, which are linear, right? The simulation of the dynamic itself is not computationally expensive. What's really expensive will be the simulation of these random times. So having many more random times to simulate makes the algorithms really expensive computationally compared to the isotropic version of the target, right? That we have for rho equals 0. But it's not really, it's not only a problem of computational cost, but we can also see a performance degradation. So here we have on the y-axis the root mean squared error, and we can see already for both algorithms that this performance measure is really going the wrong direction, right? As we increase the correlation. And in particular, this has more or less the same effect on both samplers. But we can see maybe already that zigzag is a bit more affected. And this is even more true when we consider the radius statistic. So again, the two processes really start from different values. So the zigzag sampler, we know actually also from the theory that performs better for independent Gaussian, an independent Gaussian target for the radius statistic, which is just the sum of the squared components. But then we see that the error that's made by the zigzag sampler increases quite steadily as the correlation increases. On the other hand, the bouncy particle sampler is more robust in a way, but still starts from a less accurate estimate for the radius statistic. So we have basically already seen that it's not just a problem of computational cost, but it's combined. This is combined really with a degrading performance of the two algorithms. And so what can we do to make these algorithms better in such cases? Well, what we can do, for instance, is say we are given a suitable transformation matrix M. And so we have our starting target density pi, which is anisotropic, and we apply the inverse transformation, right? So the inverse of M to the state space. And if M is chosen in the correct way, what will happen is that we will obtain a transformed target pi tilde that will be more isotropic, if you allow me to use this expression. So more isotropic, by that I mean it has maybe not as strong correlations or rescaled axes to make the variances unitary. So in this case, it's really good to have in mind a unimodal target density, I would say, to just understand what we mean by this. And then we know that these algorithms have quite good properties on isotropic targets. And so we can just, once we have obtained this transformed target, we can run the samplers that target pi tilde, and we will obtain our continuous time dynamics, capital psi t and capital theta t. But then, of course, this will be invariant with respect to pi tilde, and we want a sample from pi. So the last thing to do will be to go back to the original space, applying the M transformation in this case. And as a consequence, we will have our continuous time trajectories xt theta t. And this will be a sample, right, approximately from pi, or asymptotically from pi. Okay, then say we are given a matrix M. We would like to understand a bit how this process actually behaves, because this will be a linearly transformed zigzag process or bouncy particle, depending on what's our choice in this setting. Here we consider just a zigzag process, which we will use now as an example. So we can derive the Markov infinitesimal generator of the process. And for those who are familiar with the generator of the zigzag process, they can easily see the differences maybe, but for those who are not, the main difference, actually the differences with respect to a standard zigzag process are really here and here. So here basically we have the velocity of the vector of the process, which usually is theta. Here we have an m theta. So the velocity of the original process gets transformed. On the other hand, here we have the switching rates. So these are really the rates of the inhomogeneous Poisson processes that give us the random times. So the times of the events, of the random events. And this will have this expression. What's also interesting is that we have really a new set of velocities that can be taken by the process. So usually the process can have either velocity +1 or -1 in each direction, but with this transformation scheme, this changes and we have a whole really new set of velocities. So two differences between this preconditioned zigzag process and the standard one. We have different velocity and different switching rates. Okay, and then reasonable choices for this matrix M can be as written in this slide. So we can, for instance, take M to be the diagonal matrix, right? So what we have is on the diagonal, we have the square root of the variances. And this really corresponds to a rescaling of the axes. Alternatively, we can take M to be a rotation matrix. But the problem with this choice is that at the moment, there is no theory for this. We don't really know what's the optimal angle of some even unimodal target density. So it's not really practical at the moment. The third option is really to estimate the full covariance matrix and then take its square root to be our transformation matrix, right? So in this case, what happens is that the covariance matrix of pi tilde, so of the transformed target, will be the identity matrix. So this is, let's say, a full transformation of the target. The point in any case, for any of these the choices, is that beforehand, in common applications, we really do not know the covariance matrix nor the variances. What we can do to overcome this issue is really to let the samplers learn the covariance matrix or parts of the covariance matrix on the fly. So while the process explores the state space, we make it learn the quantities we're interested in, and iteratively we implement them. So we change the Markov transition kernel or a Markov infinitesimal generator of the process. And this, of course, defines an adaptive scheme. But then there's also a bit of an issue in the sense that what's an adaptive scheme in continuous time? And so one way to see this is really by introducing a grid of points for the time variable at which the transformation matrix is updated. To this end, we can select a time step delta t, and we can iteratively follow the algorithm in this slide. So we have an input, a family of kernels, calligraphic P. We can imagine this can be a family of preconditioned zigzag processes or preconditioned bouncy particle processes. We then will have to give to the algorithm initial conditions x theta, initial condition m for the matrix. We will need, for theoretical reasons, a set B, then a delta t, which is our time step as we have said, and a number of iterations n. In output, we will have a sequence of discrete samples. What we will do then is, while we don't exceed the prefixed number of iterations, we will obtain the next position and velocity of our process, so xn plus 1, theta n plus 1, by simulating this, well, actually discrete time Markov transition kernel, or if you wish, this is actually also a continuous time Markov kernel, but we will basically simulate for a time step delta t. So we start from the previous position, we simulate the process for a time delta t, but this is not a standard zigzag process, nor a standard bouncy particle process, but actually it's a preconditioned, either ZZS or a BPS. And the preconditioner is our current estimate for this transformation matrix, depending on what we have chosen it to be. It's important to observe also that there's no discretization error introduced here. We can really do this step, simulate this this step exactly without any discretization error. We're just introducing this this grid. But this is really to have the adaptation, to introduce this adaptation. And then again, we have introduced this set B. If the process at the time step n+1 is inside of this compact set, then we will update our adaptation parameter. If not, we will not do that. We will store the information and update it as soon as the process enters again into this compact set. And this is really a trick that makes the theory and proving things for adaptive MCMC algorithms easier. But so about the theory, really, what can we say, for instance, about the adaptive zigzag sampler that we have introduced? Well, let's consider these assumptions. So we have the following growth conditions, which are the same as in Birken's, Roberts, and Zit. And under these assumptions, actually, we have a geometric ergodicity of the zigzag sampler. And that's why we choose them. The second assumption is on the design of the algorithm. So we will require the excess switching rates to be strictly positive and bounded by above. This is just really an assumption on the design of the algorithm. And I think it's also interesting to say that probably it's not necessary to take the excess switching rates to be strictly positive. But of course, you can imagine this makes things a bit easier to prove. The second assumption is that we will take the calligraphic M to be a compact set of invertible matrices. So again, this is an assumption that will facilitate proving theoretical results. And finally, as we have also already said, adaptation can happen only if the process is inside of a user-defined compact set B, which can be as large as we want. So it's again, probably not necessary, but it's useful when proving things. Under such assumptions, we can take a delta t strictly larger than 0, consider our family of preconditioned zigzag processes, and with such conditions, we have ergodicity of the adaptive scheme, which in the context of adaptive MCMC means what's written in this slide. And this is true, of course, also for all initial conditions. In addition to that, we have also a weak law of large numbers for bounded and measurable functions. Okay. So the same idea, of course, can be applied to the bouncy particle sampler, and this will define an adaptive bouncy particle sampler. The same theoretical results can actually be obtained. I'm not showing them here just because it's. I think I just want to give you the idea, but really the same kind of result holds, and the assumptions that are needed are just standard assumptions under which the standard bouncy particle sampler is geometrically ergodic. So actually, we don't need anything more than that to have an ergodic adaptive algorithm. Another thing that I would like to really underline is that the theorems hold for any choice of the discretization step for the time variable. And so I think this is a nice feature, right? So we don't, there are no conditions on delta t. For any choice of delta t, we have ergodicity and correctness, so of our adaptive algorithm. A further adaptation concerns the bouncy particle sampler, and in particular the refreshment rate. So I haven't mentioned earlier that there are two possible things that can happen at event times for the bouncy particle sampler. So either the particle gets, the process gets reflected on the contour lines of the energy function, or we draw from for instance, a standard Gaussian distribution just to refresh, really, literally, the velocity. And well, this will have a rate, this event, a rate of its own. And in general, until now, the user had to choose this rate before running the algorithm. But actually, there is now an optimality criterion obtained in Birkins, Kamatani, and Roberts. And what we can do is really apply this optimality criterion while the bouncy particle sampler runs, and so while the process explores the state space. And this really gives a further adaptation for the BPS. And more details on this will be in our forthcoming paper. Okay, now we have discussed about a lot of things, but I think what's really interesting is really if these adaptive algorithms actually work, right? Because if they don't, it's not so useful. And consider again the same example as before, the same example we used as a motivation at the beginning of this presentation. Again, we will consider different values of rho. Here we consider a larger time horizon because we're interested really in having accurate estimates, and we run 50 times the samplers. We choose delta t to be equal to 1, and we have an adaptation that takes place every 1,000 time steps. So here we have the average ESS per second of the zigzag sampler against the adaptive zigzag sampler. So again, as we have said earlier, the zigzag sampler experiences a performance degradation for an increasing value of the correlation. What we can see actually is that the adaptive zigzag sampler maintains the same performance. It increases in variance. I mean, the estimates really increase in variance, but still we have a much improved performance. The same thing can be said if we consider the radius statistic. So the plot really says the same thing. The adaptive zigzag sampler remains, it has more or less the same performance independently of the correlation, whereas the zigzag sampler really gets worse. Now, let's see a bit bouncy, what happens for the bouncy particle sampler. Here we have in red the standard bouncy with a refreshment that equals 1. In green, we have an adaptive bouncy, refreshment equals 1. And then in blue, we have adaptive bouncy, but with adaptive refreshment rate. And here again, we see the performance of the bouncy particle sampler. This is average ESS per second for the mean, right? So performance of the bouncy is getting worse, whereas its adaptive counterparts have the same performance, more or less independently of the correlation. Same plot, but for the radius statistic. And again, here we see an improvement really of the adaptive schemes. So what we have seen is that PDMC algorithms can have really worse mixing properties or bad mixing properties when we have an anisotropic target. And what we tried to do was to introduce an adaptive scheme to improve this aspect, right? And we have seen that at least for a very particular, so for a multivariate Gaussian target density, this can have quite strong improvements, can lead to a better sampler, a more accurate, and this problem in a way can be tackled. We can also imagine that if we have to learn the entire covariance matrix, this will be particularly effective for a target with moderate dimensionality. Moreover, subsampling techniques are particularly interesting for this class of methods, and the same idea discussed in Birkins, Fernhead, and Roberts can be applied to the proposed adaptive schemes, right? So this makes this adaptive scheme interesting also for the case of data sets with a large number of observations and moderate dimensionality, possibly. In particular, because we know, I mean, that the adaptive scheme we have considered is particularly interesting for unimodal targets, and we know of the asymptotic normality of posterior densities in Bayesian analysis. So in this case, when we have a large number of observations, this scheme can really prove to be a valid solution to this issue of anisotropic targets. Experiments for this are being conducted at the moment, and so I cannot really give you many details on empirical experiments. So I would like to leave you with the references for this talk. So we have all the papers that I cited or that are really relevant for this talk. Thank you for the attention, and if you have any questions, really don't hesitate to reach me in any way, either with a Q&A session or by email. Thanks again, and bye-bye.